So we're going to look at numbers in a bit more detail. Start off with the real numbers. I mean, they're the numbers that we work with. So if you imagine our set of numbers, so the real numbers. Now, any real number can be placed on a number line. The symbol for real numbers is R, but it's the hollow R. R, of course, for real. Inside the real numbers, we have the rational numbers. Rational numbers, symbolized Q. Q, that's interesting. The reason it's Q stands for quotient, and a rational number is any number that can be written as a fraction, where both the numerator and the denominator are integers. Okay, so then we have the irrational numbers. They're the ones that we can't write as a fraction. Now, as far as a symbol for irrational numbers, there's not actually a symbol for it, but a way you can represent it is R, so the set of real numbers, backslash, and the backslash means not including, and so then Q, the rational numbers. So if you've got all the real numbers but you exclude the rational numbers, you must be left with the irrational numbers. Okay, inside the rational numbers, well, they're all fractions, of course, but by fractions, I mean the ones that don't simplify down to be whole numbers. So there's our fractions. Then we also have integers. This one's a bit interesting. The symbol for integers is Z. Where on earth does that come from? It actually comes from German. So Zahlen, that's German for integer. So we use Z. And I guess we go for that because if we used I would be real easy to mix up with irrational or imaginary. I mean, there's another set of numbers called imaginary ones. So Z, we don't have any confusion there. Inside the integers, we have the natural numbers, symbolized N. What are the natural numbers? Anyone know what the natural numbers are? Or the counting numbers? Yeah, so yes, sometimes you'll see the natural numbers called the counting numbers. So the integers that are, as you said, greater than 0. Why is it greater than 0? Because I guess if I said to you, start counting, you'd go, oh, 1, 2, you'd start at 1. So there are natural numbers. 0 is still an integer, of course. It has its own little set. It's a very weird number, 0. But then over all these, you have the negative numbers. You can have negative fractions. You can have negative integers. But notice it doesn't overlap the natural numbers, because negative 1's not a natural number. And 0, you can't have negative 0. That's a bit weird. You can have negative irrational numbers, though. So that sort of overlaps. So there's our set of numbers that we work with. Prime factors. We actually talked a bit about that yesterday, some of us, when we were looking at a question. So every single number, or I should say natural number, every single natural number can be written as a product of its prime factors. So for example, 324, we could break it down 4 times 81, but those two can both be broken down, and we end up with 2 squared times 3 to the power of 4. So it's broken down to its prime factors. Highest common factor. Right, how do we work out a highest common factor? So you work out the prime factors of both numbers you're interested in. You pull out the common factors, and watch this one. So we've got 1176 and 252. 1176, it's 6 times 196, 3 times 2 times 49 times 4, so we can keep going. We end up with 3 times 2 cubed times 7 squared. 252, 4 times 63, 4 times 9 times 7, 2 squared, 3 squared, and 7. So now we pull out the common factors. So 2 squared is in both, has to be in both. So I don't grab 2 cubed because 2 cubed is not in the second one. So it's the lowest power we want for this one. 3, the lowest power we've got is 1, and 7, the lowest power we've got is 1. So the highest common factor of both is 84. So that's the biggest number that goes into both of them. So it's the lowest power, lowest power. Lowest common multiple. So again, we would write it as its primes, but now we'll write down all the factors without repeating. 48 and 15, I picked 2 small numbers here. So 48, 16 times 3, 2 to the power of 4 times 3. 15 is 3 times 5. So this is the one, like a fraction. If it's not there, put it down. So 2 to the power of 4, not there, put it down. 3, not there, put it down. I go to the next number. 3, oh, it's there, I don't have to worry about it. 5, not there, put it down. So the lowest common multiple is 240. So that's the smallest number that both of these two will divide into. Divisibility tests. All right, no cheating now, because I know it's written on the sheet in front of you. We mentioned 3, you remember, in a problem we were looking at, was it yesterday? I think it was. So if you get in quick, you can get the easy ones. How do we know if a number is divisible by 2? It's even. Okay, if we've got an even number, we know it's divisible by 2. Who's got a good memory? How do we know if it's divisible by 3? Right. All the digits will add to be a multiple of 3. 4. Yes. Last 2 digits are divisible by 4. All right, as I say, if you get in quick, you get the easy ones. 5, anybody? Right, ends in 5 or 0. 6. Right. The 6 is divisible by 3 and 2, so it must be an even number where its digits add up to be a multiple of 3. So it satisfies both of those 2 tests. Now, I'll be very impressed if you get this one without looking at the sheet. This one's very tricky. 7. Does anyone know the divisibility of 7? Here it is. Double the last digit, subtract it from the other digits, and then that answer should be divisible by 7. Give me a number that 7 goes into.
49.
Okay, I was thinking maybe a bigger one, but it'll work. 49, so what did we say? Double the last digit. The last digit's 9. Double it, we get 18. Subtract from the other digits. Well, the other digits is 4. We end up with negative 14. And 7 goes into negative 14. So that is how you test whether a number is divisible by 7. Say, not one of the ones people tend to remember, that one. 8. Yes, so it's similar to the 4 one, but now we look at the last 3 digits. 9. It's similar to the 3 one, because of course 9 is 3 squared. But this time, the sum of the sum of the digits is divisible by 9 this time instead of 3. 10, anyone? Okay, ends at a 0. Here's the next one's another one that you may or may not. 11. What are you saying? What? You are right. It has something to do with every second number. The sum of the even position digits equals the sum of the odd position digits, or they would differ by a multiple of 11. So give me a number that's divisible by 11. Maybe make it a little bit longer than just 2 or 3 digits. We have 49,984. So the sum of the even position digits. By that they mean that's in the second position, that's in the fourth. So 9 and 8 is 17. 4, 9 and 4 add up to be 17. Therefore, the number is divisible by 11. Fractions and decimals. Being able to convert between them. We're going to look at this one in particular. Converting recurring decimals into fractions, because to convert a fraction into a decimal, quite easy, because you just do the division. So 3/4, you do 3 divided by 4, and what do you know? It comes out to be 0.75. So going that way is usually easy. Going from fractions back to decimals. If it is a terminating decimal, again, easy, because we have this lovely base 10 system. So if it's 0.321, we know it's going to be 321 over 1,000. But it's the recurring ones that are more interesting. I'll start with one that we should know the answer to. 0.6 repeater, 2/3 by the way, in case you didn't. So that is 0.6666666, and it just keeps going to, forever. So we can do it via simultaneous equations. We'll let x equal 0.6 repeater. So in other words, it is 0.66666666666, and so on. Now the thing is, by creating these simultaneous equations, I want to subtract the thing that's causing the problem. And the thing that's causing the problem is all those repeating digits. So if I multiply by 10, I'll get 6.6666666. But now I can subtract and get rid of that repeating part. So when I subtract, I'll get 9x is equal to 6. So x is 6/9. So 0.6 repeater is 6/9, which of course simplifies down to be 2/3. So 0.81 repeater, same idea. That one is 81818181818181. So if I let x equal that, but I want to get the same thing after the decimal place. So multiplying by 10 is not going to work because I've got 0.818181818181. If I multiply by 10, I'm going to get 8.1818181818, not the same. So I'll multiply by 100. And now the bit after the decimal place is the same. Subtraction, 99x is 81. 81 on 99, that does simplify down. We get 9/11ths. What about if not all of the numbers are repeating? So 0.327 repeater is 0.3272727272727. Still the same idea. I want to subtract the problem. So if I let x equal 0.3272727272727, if I multiply by 100, I'll get 32.727272727. So the repeating part matches up. I can do a subtraction. 99x is 32.4. Well, it's unusual to see a decimal on the top of a fraction, but if I multiply top and bottom by 10, I can fix that. I get 324 over 990, 18 on 55. But if you notice the pattern, there is an easier way. Remember 0.6 repeater? I can just look at that and say, oh, that's 6, because 6 is the number that's recurring, over 9, because there's one number recurring. So there's one number recurring, I'll put a 9 in the denominator. So it's 6 over 9, 2/3. So in other words, 0.1 repeater is 1/9. 0.2 repeater is 2/9. 0.3 repeater is 3/9. Which of course means that 0.9 repeater is 1. Okay. It is true, by the way. 0.9 repeater is actually 1. 0.81 repeater, I can use the same idea. 81, because 81's the number that's recurring. And on the bottom, I put 99. 2 9s, because there's two numbers that are recurring. So I get 81 on 99, 9/11ths. So now if I get something like this, 0.7134 repeater, I don't have to muck about with those simultaneous equations. I can say, hang on a sec, that's 7134, they're the numbers that are repeating. There are 4 numbers repeating, so the denominator will be 9999. Simplifies down. If you don't believe me, get your calculator and you'll see that it does that pattern. What about the one where not all the numbers were repeating? 0.327. How do I look at that and get the answer? And this is how I do it. Well, the top's got to be 324. 327 minus 3. Subtract the number that's not repeating. So I got 327 minus 3. Bottom of the fraction, 990. 2 numbers recurring, so I put down 2 9s. But one number is not recurring, so I put down a 0. 990, and there's our answer. So if I had this one then, 0.1096, but only the 9 and 6 are recurring. So in other words, 0.109696969696, I know the top is going to be 1086, because that's 1096, minus 10, the number that's not recurring. And on the bottom, 2 9s, 2 0s. And there's the answer, which simplifies down, there it is, 181 on 1650. So much quicker than playing around with all that algebra. So if you recognise a pattern, beautiful. Use it to your advantage. 2A will start us off. Also, I've chucked some questions out of the old textbook that weren't in the new one. But again, I think I photocopied that and it's at the back of the sheets there.